we're going to talk just real briefly about the chemical potential that I was describing last time. Had a good question to start the day here. Something I really glossed over and didn't spend much time on. I don't think you really need to know the nitty-gritties of the derivation here, but since I was asked about it, I'll try to give a little better explanation. And then we're going to get into that caveat we talked about like activity. How does that work? We're going to do some calculations with Gibbs free energy just to calculate, okay, what is the Gibbs free energy or what is the K given these values? So we're going to do a few practice things, hopefully make this a little more tangible today. Say, okay, what are we doing with these equations? So going back to last time, this little v here was part of the question, like how does that go into this quotient thing here? And the v was really almost like a matrix of the subscripts or the prefixes. So when we said A plus B, blah, 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 the v for, we could say like VA has some value and VB has some value, and then VI or the sum of VI would be capturing each one of those. So as we go through the list, we are putting them all together into one unit. That's the summation here. So when we're doing the delta G for a reaction, it's all of the A and the AA, the BB, all of that. The little v there is accounting for the lowercase letter. So that's kind of where the v is coming into. So when we sum VI, that's going A, B, C, D. So that's just a way the way the derivation is going is we're saying all of these components are going into this. So we're taking the molar amounts times the chemical potential to get the Gibbs free energy. Because the chemical potential was kind of like temperature. It's like there's some amount of energy there, but the temperature of one little tiny drop of water, even if it's boiling hot, is not going to give you a severe burn, right? But the temperature multiplied by a whole liter of boiling water will burn you pretty severely, right? There's a difference there, even though the temperature is the same. The G is the temperature times the mass or the volume, right? The mu is just the temperature. That's the type of property we're dealing with. So then we have to multiply the mu by the amount, the molar amount, and that's the little v is giving us that kind of that information, at least on a stoichiometric basis. Okay, so that all collapses or condenses into this Q, which is our quotient, and that was how we can say, well, if we're at equilibrium, then what we're saying is that delta G is 0, and we can simplify some things, and that Q turns into K. So if we're at the standard conditions, that means we can define it all that way. Delta G equals 0 at equilibrium, then Q is equal to K, and we get these equations. So that's all coming from those little V's. All the V's then give us that Q, which is all that. Okay, so that's kind of where we left off last time, and I basically was trying to highlight that we have a few key equations that we can use, and the general principle that, you know, from a moment ago, essentially delta G is for a given species is going to be mu times, or I'll say n times mu. So the number of moles of that species times its chemical potential. Okay, so we have that relationship and these other formulas, and we can put them to use. Okay, so that brings us to one other thing I did want to talk about with the chemical potential is kind of an interesting little fact or interesting thing to consider. So when we're talking about the chemical potential, we talked about it as if it was like putting a ball on a staircase, right? And you could bring it down or you could bring it up, but you just say, okay, some level's the ground floor and then you're going up or down from there, right? Well, in practice, that that staircase can go down pretty much forever, meaning you can get smaller and smaller concentrations closer and closer to zero. So if you were to do that, and you have very, very low chemical potential, well, what happens to our equation here is the activity. So A here for I is the activity. We can kind of relate that. I mean, this equation is relating that to mu. Activity is essentially the concentration of A, the molar concentration, but we can multiply it by the activity coefficient that we'll talk more about soon. So let's just imagine that's 1, then the activity is the concentration. So if this number is really, really small, if A is very, very small, then what happens to this term? Well, the chemical potential of the reaction or the system here is equal to the standard potential plus whatever this term is. And if that A is really, really small, then the natural log of a really, really small thing turns out to be, so if you do natural log of 0.0000, lots of zeros, and 1, so you could be saying e to the what equals 10 to the minus 19th. Well, eventually, this entire term can be so small that that right side of it makes this a negative value in total. If it's a very unlikely, and the way this is relevant is if you have something that's very insoluble, so something that like almost never dissolves, like quartz. It's like almost insoluble in water. But if you put it in water, there's a tiny, tiny, tiny bit of it that will dissolve. That's where this takes place. You might have heard the term diamonds are forever. I hate to break it to you, but they're not really, because of this type of principle. There's a tiny, tiny bit of it that will oxidize with oxygen in the atmosphere. Or it will go from a crystalline structure into an amorphous structure very slowly, very tiny bit over time. And so the half-life of a diamond in our standard atmosphere is actually something like 500 years. So in 500 years, your big diamond that you bought and cherished, maybe half its size. I might be off on that, but it's on the order of hundreds of years, maybe 1,000. So it's not forever. So maybe look into something like sapphires are a little more forever probably, but even them, depending on what's around. And you can imagine this feature is actually why it's really, really hard to get a very, very ultra pure substance. Like if you're like in a lab, you'll see 99.99% pure or whatever. Or if you're looking at gold and what's the purity, it's really hard to separate things completely from everything else because of that activity, the way the activity works. So it's just a little kind of an interesting side note. It takes eons and eons to really dissolve a meaningful amount of quartz, but rivers and streams will do that over a very, very long time. Most other things would dissolve first, but there will still be a little bit of silica coming out, or whatever the case may be. So some minerals, it's extremely slow, but still something there. Okay, this here is just a table to kind of show a few species and their activity, now their chemical potential. If we write it as delta G of formation, so the Gibbs free energy of formation, if we write it as per mole, that means it's essentially equal to, for 1 mole of it, that's equal to the standard chemical potential for that species, right? Because I mentioned, and we should have a better thing for this maybe, but standard Gibbs free energy, I'm going to say of formation in this case, will be equal to mu, the standard potential, chemical potential of formation times the number for that given species. It's the number of moles. So if the number of moles is 1, as in kilojoules per mole, then that's going to be the same. Okay, and this is the little standard is meaning we're at standard conditions, which is 25 Celsius in 1 atmosphere. We often call that standard temperature and pressure. Okay, so mostly I just am showing you this to give you a feel for the types of numbers we'll see. You know, negative 33, negative 200, negative 300, positive 16. And then we have a 0. And that one I do want to highlight because we actually define hydrogen, a few other things, but hydrogen in particular, H+, aqueous hydrogen with one, it says molal, we'll call it molar because it's approximately the same. So we could be more precise, but approximately 1 mole per liter of hydrogen we are defining as 0 for that standard potential or standard Gibbs free energy. Now we do that because we have to have something to compare everything else to. Remember how we talked about the staircase? We have to define some spot as 0. Well, this is the way we do it, is we're going to say that energy of formation for hydrogen, the aqueous hydrogen, H+, that's going to be our 0, and we can compare everything else in chemistry to that. And that gives us a very standard and convenient way to move forward. So in a way, this is arbitrary. It's an arbitrary standard, but it's also one that makes a lot of sense. Hydrogen is the first element, and there's so much that goes on with hydrogen. It kind of makes sense that we do that, and that sets the stage for everything else, because we can compare any other reactions and derive some relevance to hydrogen, especially in the world of aqueous chemistry. Maybe something doesn't react with hydrogen itself, but it's going to react with water or have some interaction with it in some way. And so we can find or derive its energy based on the fact that we have defined this one. So once we define that one, we are good to go for kind of everything else and derive each one of these. So we'll see more of these in a practice problem as well. All right, so I'm going to get you thinking here. You'll see this is a problem I took from a book. This is one of the, I don't love that book, but this is a simple enough problem, I think. So we'll take a look. And I have a couple of those equations here to remind you. The problem says the chemical potential for H+ at 10 to the minus 5 moles per liter is Y kilojoules per mole in a certain one-phase aqueous system. The volume of that system is 5 liters. And then it says write the expression for G for H+. We don't know Y, so leave Y in your equation. But just see if you can write out G equals what? And you see the solution itself is quite short, right? It's just writing it out. So give a moment of thinking to that. So hopefully with the equations or with memory, you remember a minute ago I was saying, well, G is basically the number of moles of something times its chemical potential, right? So when we go to answer this, we're going to use that form and basically say, well, we have some moles per liter and we have some number of liters, so we can find the moles and get our answer, right? So when we reveal it here, that'll be 10 to the minus 5 moles per liter, that capital M is moles per liter, times 5 liters, times Y is that energy value, the mu, right? So what we needed to know is the chemical potential, mu, equals y. And so then G is going to be equal to the concentration times the volume to get us to moles. So this will be moles per liter times liters times mu, essentially, right? Okay. So that was just the little process there, kind of putting these pieces together a bit. Does that make sense? Okay. So here's a little fancier one, kind of building on that topic that I was mentioning about the activity. And we haven't really talked about solid phase stuff, but I think the chemical potential will still work just fine for us. I don't think we need to get too worried about that. So this problem says for a reaction that is essentially gold, so the chemical potential of gold, so we have mu gold equals the mu standard gold plus RT ln of A, activity of gold. In this situation, if we have the activity of silver in gold, so we've got some, this is each mu here that has a subscript of silver and a superscript of gold. So, and I forgot to bring over the equation. I might go find that in a second. But essentially, gold and silver like to mix. And so this is going to be some reaction of trying to get gold separate from silver. Ag is silver, and Au is gold from the periodic table, right? Okay, I'm going to finish reading it, and then I'll see if I can pull up this reaction. So if the activity of silver in solid gold, which is that activity term there, is measured on the mole fraction scale, what is the value of RT ln of A at 25 Celsius when that activity is 10 to the minus 3, 10 to the minus 13, and 10 to the minus 23? And we're given a value for R. So that's part A. It says mole fraction, just treat that as a concentration. That really what that means is moles of silver per moles of total substance. So don't worry too much about it. Just see what you can do, and we'll look at the solution. I'm going to pull up this book and find that. just show you real quick. This particular book is where I got it from. It's saying delta G is equal to mu of silver in solid gold minus mu of silver in the surroundings, which is a very small number. It's saying a lot less than 0. So I'm going to write that up. Do you feel like you got an answer for part A? Okay, so let's take a look. So if we put in those numbers, RT ln of A, and we take those A as 10 to the minus 3, 13, or 23, we get these values, and that's really all A was asking for, is put in those numbers to the RT ln of A. Now, part B says since the chemical potential for silver in solid gold, or excuse me, at a standard state is a finite number, so that's this is finite, is what it's saying. You just calculated this in part A, and we see those are negative numbers, negative 17, 74, and 131. So given that that's a finite number, how does this trend affirm what we said about chemical potential in general in terms of it's difficult to separate them? What can never be 0? Delta G, or the chemical potential, meaning so meaning this part or this part? Yeah. Okay, so the chemical potential for the system, so you were asking, does that mean it can never be 0? Well, let's just say this is some number, right? We could look it up probably, but let's just say it's 50. Okay? What does this trend tell about it then? If we say 50 plus negative 17, where are we at? It's a positive number, right? If we say 50 plus minus 74, suddenly we have a negative number, right? So now suddenly it's a favorable situation. Like the delta G, the chemical potential is a negative value now, right? So the smaller we go with that activity, eventually we reach a spot where the net is a negative. So we could even put this to 500, and we can see the trend will eventually lead us, if we get a small enough activity number, will get us to the point where the chemical potential is negative, right? So that's kind of what we're thinking here. So the smaller that this activity of gold becomes, the smaller that the chemical potential will become, because the value of the standard condition is a constant, right? So that's the key here. The standard condition is a constant. So if we're defining the chemical potential of the system as the standard plus the current situation, so the right part of the term is the current situation over here, then eventually we can get the entire thing to be negative, or it will become negative. Okay. Does that make some sense? A little bit? Okay. At least it's some kind of showing a few numbers here, I hope. All right, so this one I left on some notes from last time. It's a little more complicated of a problem. So We'll see. I haven't taught you anything about gas phase stuff, and I think this is touching on it. So don't worry too much about it. We will cover this later in the semester, but you've probably seen this stuff before. So we're gonna go through this one and make some more sense of it. Then we'll move on a little later to some things that are a little more straightforward. Okay, so this one says, compute the value for delta G standard at 25 Celsius for the reaction by which gaseous oxygen dissolves in water, namely oxygen gas going to aqueous oxygen. Okay, so we're gonna take a moment. Like I said, I haven't taught you this exactly, but we're gonna consider that this is gonna be the reaction. So oxygen plus water is going to oxygen and water, right? But it's converting from the O2 form to the O2 aqueous form. We would need a table telling us something about these standard potentials, or the Gibbs free potential formation. So from the table 2.2, we know that delta G of formation is 0 for oxygen gas. That's the standard condition for molecular oxygen in the gas phase. So think about what we would need in order to get there. And just for a moment, we'll take a look at the solution. All right. So first, we can remember that our delta G equation is essentially delta G is equal to delta G naught plus RT ln of K. At equilibrium, we are defining the delta G as 0, right? That's when there's no change in our Gibbs free energy. That's our equilibrium state, right? So delta G equals 0. We also know that for the oxygen side of things, the gas side of things, we were told the delta G formation, or we could have looked it up, I guess, but I went ahead and showed this. That's 0 for the oxygen. Okay, so that's pretty helpful. But before we look at exactly how they were writing this up, one thing we can do if we know that we're at equilibrium is this equation, if this goes to 0, that gives us delta G naught equal to negative RT ln K. So we can set up something there to start solving. Now K, the rate constant, that's the A times B over C, that's the products over the reactants. So I said that backwards. That's CC times DD over A and B. So we can set that up for a reaction that's oxygen, gas, and water. The waters go to 1 because it's liquid water. The activity is 1 is kind of how we treat that. And then it's the oxygen over the oxygen. So that's going to be our K. The other way to write it is simply delta G is for the system is going to be delta G for the products minus delta G for the reactants. Okay, that's the simpler way to deal with it. And that's what the solution is doing, is saying, okay, well, delta G naught then should be the products minus the reactants. And I think this is coming from a lookup table. So if you were getting stuck at what is this value, we'll just say that's coming from the table. I should have given that to you. But what we see here is that since delta G for formation of oxygen gas is 0, this term is 0, so it just becomes the delta G for oxygen aqueous system. Okay, so we didn't actually need to know a whole lot aside from just if you had the lookup table, right? But what we do need to recognize is that delta G, and we can do this at standard or under a particular condition, whichever way, the delta G for the reaction, we'll say, is always going to be the products minus the reactants. Okay, so we can, if we want to, we can solve that with the thermodynamic coefficient stuff, or we can, if we have the values, we can say, let's just do products minus reactants. Okay. All right. So part B says, what are the units for the equilibrium constant? And that's where this little derivation I did might help us a bit to say, okay, well, we have concentration in the aqueous phase divided by some concentration in the gas phase. And here, like I said, we're going to cover this in more depth later, but when we work with something in the gas phase, we don't use a molar concentration typically. We usually use atmospheres is the SI unit, right? So atmosphere being, 1 atmosphere is the amount of pressure at sea level, so approximately what we are experiencing right now. And if that was pure oxygen, that would be 1 atmosphere of oxygen, right? So that's the situation. So this would be molar units or maybe molal units per atmosphere. So M per atmosphere. Oh, that's part C. Okay. And that's where this is coming from. Okay, so then part C says, okay, use the value that we got in part A to compute the K value. And this is something you should be able to do, right? So use this value, the 16.52 kilojoules, to find K. Okay, so this should hopefully be plug and chug. We have delta G naught equal to negative RT ln K. Now we can change that if we wanted to a natural log. That gives us a conversion factor. But you could also just keep natural log. That's fine too. So they wrote it up that way, negative 2.303. That converts the natural log to a log, base 10. So then you can say log K equals that value, and then calculate from there. So put in the numbers. It should give you 1.27 times 10 to the minus third, and the units there are molar per atmosphere, or molal per atmosphere. Okay, is that fine? Any issues? All right, so last part says when the total air pressure is 1 atmosphere, the pressure of oxygen is 0.21 atmospheres. For that value, so that's kind of like practically speaking what we breathe, instead of having 1 atmosphere of oxygen, we have 1 atmosphere of our atmosphere. What is the concentration of oxygen aqueous in molality and in milligrams per liter? So just answer in molarity. Don't worry about the molality stuff. For molality is 1 mole per kilogram of water, and so we need the density of water at 25 Celsius, which is slightly under. So it's very close to molarity. We're just not going to worry about that. The solution will do that, but calculate that for molarity. And I'm going to trust that you could also calculate it in milligrams per liter. For the sake of time, I'll say do it on your own if you like. And I'll tell you that typically at room temperature, it's somewhere around 8 milligrams per liter. So if you get an answer of 80, you're wrong. If you get an answer of 0, you're wrong. It should be somewhere between 7 and 10 at room temperature. Like a cold trout stream that's close to freezing is going to be something like 15 milligrams per liter. A warm, stagnant bayou in the middle of the summer might be like 3 or 4, depending on how much oxygen demand is there. Okay, so I'm going to flip back and find that K value we just got for you. 1.27. Okay, so hopefully you can see that the answer here is simply going to be, we set up the equilibrium equation. The K is equal to oxygen aqueous divided by oxygen gas. And then we can multiply both sides by the concentration of oxygen in the gas phase. We were given that's 0.21 atmospheres, so we could even call it atmospheres. Multiply that by the K value that we have, and if we keep the units appropriately, we'll recognize that that's multiplying atmospheres by molal per atmosphere. I guess we're already in molality, so I don't know why I bothered with that. We'll leave it as molality rather. So that's just going to be 0.21 times 1.27 times 10 to the minus third. And that should be our answer, right? So that's what we see here. And we get a value of 2.67 times 10 to the minus fourth moles per kilogram. They do the conversion and say, okay, that's also 2.7 times 10 to the minus fourth moles per liter, right? Like I said, a liter of water is very close to 1 kilogram. Okay, then it does the conversion. So if you wanted to test that on your own, make sure you do that. Just ignore this part, but we see the answer here is 8.55 milligrams per liter, right? So just as a double check, you know, common knowledge with a pure water, it should be, like I said, somewhere 8 to 10-ish at room temperature. Now, some things could affect that because it could affect this equilibrium constant if you have a lot of salt in it, a lot of chloride. Certain things affect how that happens. Okay, one more practice problem here. We're going to calculate the solubility product. So KSP, this is just another equilibrium constant. We're going to do this for gypsum at 25 Celsius from the tabulated data provided here. And the reaction is gypsum, which is calcium sulfate, CaSO4, with 2 waters. So when you see this little dot, that essentially means we have some solid here that the crystal itself or the salt or whatever has some water in it. So for each molecule of gypsum, we have 2 molecules of water stuck in it in this solid form. Okay, so that's going to be in equilibrium with calcium, sulfate, and water. because I put the wrong thing there. That's all.
So is it supposed to be hydrogen peroxide in the equation, or is it supposed to be water on the table?
It's supposed to be water on the table. It's a very good question. Why did I circle hydrogen peroxide? Because when I was preparing and I was grabbing the table here, I copied over hydrogen peroxide and meant to copy over water. That's what happened.
Okay.
Sorry about that. Good catch. I'm glad you guys are paying close attention. So I'm gonna pull up a table to fix that. So don't make my mistakes on the exams. Look at the right parts. So here's our book. If you take a look at back of the appendix, by the way, we have this table. This is what I was copying from as I was preparing, and we'll be able to scroll down until we find hydrogen. Not too far. And so I took a look here, and my brain was like, H2O aqueous, got it. But I needed this one. Oops. I'll come back. All right, so I'm going to pause this real quick and fix that. Okay. Not pretty, but it's fixed. Okay. Yeah, feel free to work together, by the way. Ask me questions, ask each other questions.
So you have to put the stoichiometric coefficient in front of the delta G standard, right?
Yeah.
You
So
don't necessarily need to do it for the water since there's 2 moles of water on the left and 2 moles of water on the right.
actually not, because on the left here, so there's a good question here about the stoichiometry. So, all right. So I'm going to say one thing real quick. When we're doing this, the stoichiometry is really important, and it's easy to make a mistake and not realize that you need to account for the number of moles here. And there's a really good question about, well, there's 2 on the right and 2 on the left. Won't they cancel, or do we need to really worry about that? But the one on the left here, that's not actually two moles of water in the same sense as we normally think about it. It would be like if we say CaOH2 calcium hydroxide, we could do the same thing here and say that's 2, right? It's kind of writing it in the same, or in a different way for the same type of a thing. There are 2 moles of water there for every 1 mole of gypsum, but this is 1 molecule total. So the energy for that one molecule is set, and those two water molecules are just with it, and we're not treating them as anything separate. It is one entity there, right? So that because it's one entity and we have a 1 here for the stoichiometry, we're not even touching water on the left side of that equation, right? That is just one molecule. So I want to make sure that's clear. But the other thing is, that does bring up the good point that we do need to account for this 2 and multiply when we, I'm a little ahead of myself now, but we need to make sure we have that. Okay, so since I'm already talking, I'll continue. Setting up this problem, first thing we can do is write up the equilibrium equation. K, in this case the solubility product, is equal to the products over the reactants. Now, because we have the 2 for the water, we would square that here, but it doesn't actually matter too much because since it's liquid water, the activity is going to 1. So 1 squared is still 1. And on the bottom, the activity of a solid, because this is an equilibrium between something that's dissolving, it's a solid, we're going to say the equilibrium of that solid is also a 1, so that goes to 1. We're left with simply the KSP is equal to Ca2 plus times SO42 minus. Yeah?
So in the future, would you expect us to put each of the species in the reaction and then just cancel them out whenever they don't apply? Or can we just like, because I had put KSP is just equal to Ca2 plus times SO42 minus.
I'm fine if you want to shortcut it. I'm just wanting to make sure you guys are clear on why you could shortcut it, right? So I'm trying to be extra explicit with how I write it to make sure you understand that. Okay, so then we don't probably need that right away, or maybe not at all, I guess, to solve for the K, or maybe some other question we might ask. But the question here is to calculate K given the tabulated data. So we'll come back to that in a minute, perhaps. But that's just immediately when I see a solubility reaction or any equilibrium reaction, my mind goes there. Let's set that up in case we need that, right? It's good to go ahead and do it. In terms of the thermodynamic aspects, we have delta G for the reaction is the products minus the reactants. So given that we can find a bunch of delta G standards here, we can work from there. We were also given that we're at 25 Celsius, and maybe we just assume 1 atmosphere. If we weren't given that, that makes it so that we're at standard conditions. Okay, so that means we can use delta G standard here and just say we're going to solve this for that scenario. So in that case, we take the products, which were calcium, sulfate, and water, not hydrogen peroxide. So good catch. We put those values in, and we need 2 times the value for water, because remember, the number of moles we have matters, and these are per mole values here. And on the reactant side, we just have the gypsum, which was a very large negative number, -7, basically -1800. Okay, so we can get all of that. I'm actually taking a little bit, so I'm taking this example from this book I showed you. This is the recommended, the smaller one. You have the access to the free one that I have on Kindle here. So the little table is coming from the library book, the one, our class book. And the problem is coming from here. So I actually have a tiny different number because they had a slight different change in the data here. So I'm going to say that this is approximately, and you can correct me here, but it should be very close to 26.28. Do you have a different number?
I got
24.71?
What was the delta G standard reaction value? I got 47.3. Because I ended up with a KSP of like 1.9 times 10 to the 8.
So let me come back to that in just a moment. But we do have some agreement that when you do the products minus reactants, you get 24.71. This is from the other book, so we're not going to worry about that. You got a different answer, and you're trying to figure out why, right?
I thought that was the KSP value. Sorry.
Oh no, this is the delta G. I went back to calculate this. Good on that? All right. So from there, we can then take a look and solve for the K. We don't have concentration, so we can't actually use the little derivation I did with the solubility product. You know, that doesn't give us really anything. So what we need to do is take it back to the thermodynamics. And that we know we have the equations we used last time. Negative RT ln K. So given that now we have that term for the reaction, this would be the solubility product, since that's the reaction we're talking about. We can solve for K. And again, there's going to be a slight difference here, but it should be very close. The number that I'm following says that's 10 to the minus 4.6. I think they did a log change, and then that became the log K was equal to negative 4.6. So that's kind of why they left it in 10 to the minus. What did you guys get for that? Did you calculate that yet? 4.69 times 10 to the minus 5. Okay. Sounds right. And I can check to see how close the answer I had. So you can see if we used the value that I had from the book, that was 2.5 times 10 to the minus 5th. So a little different, but certainly same order of magnitude. So a little change in the values here. They've probably been updated since this was published, I think 1999. So new data value, we get a new solubility product, but it's still kind of in the same realm. Okay. So I'm not even or, I'm just going to say old values. Okay. Does that make sense? Good on that? Okay. I wanted to talk briefly about, and I'm not going to get through all the slides I had today, so we'll pick back up in a little bit, but I'm going to go over this slide first. Another thing we can do with these similar calculations is say, well, what happens if temperature changes a bit? We have all these equations with, RT ln K. The T there, we can change. So if we do a little bit of algebra or one integration, we can get a way to find out how K changed when we changed temperature. So this is what we call the Van't Hoff equation, and that's what it's for. So if we have delta G for some reaction, and we go back to the thermodynamic definition to say that's the change in enthalpy minus the temperature times the change in entropy, we also have said that we can relate that to RT ln K. Well, it turns out that what we can do with that is we can rearrange it to solve for ln, a new ln, if we know the enthalpy and the entropy here with this equation. Now this equation holds true if we are pretty close to the same temperature. So if we started at 25 Celsius and we go to 40 Celsius, we can do that, no problem. If we make a big change, we can no longer use these standard conditions because those are at 25 Celsius. Right? But it's a good approximation, and we can just use the default values if we are pretty close. So that's the one caveat. We might have to calculate new delta H and new delta S. Now, the other formulation of this, and this is really what we call the Van't Hoff equation, is to say the d ln of k dt, so how does this ln of k change per change in temperature, we can set that derivative up equal to delta h divided by RT squared. From there, we can integrate that and get these equations, which is something you probably saw in chemistry at some point. And that's the kind of thing I'll give you on an exam formula sheet to say, look, here's our Van 't Hoff equation. You know what to do, right? You have temperature 1 and temperature 2. And if it's again, I think this applies actually to both here. We might have to recalculate delta H, but if we have it, and we can go from there. Okay, so that means if we had a problem where this gypsum problem suddenly said, well, what happens at 40 Celsius? How much does that change it? We could solve that problem. Okay, so I'm going to leave that either for next time or maybe put that on a homework instead. And we'll cover a couple more problems and activity coefficients next time when we return. All right, have a good day.